Hi everyone, welcome to this video. What we're going to be talking about now, like we just said before, this is a method that is kind of similar to astrometry, kind of not. So what we're going to be jumping into now is another method that is we still infer the presence of a planet based upon stuff that we see happening with the star, and we can infer and calculate properties of the planet. Now this method is what we call the radial velocity or RV method.
Yeah, you might also have heard it as the Doppler method before.
Yeah.
And so let's think back to this astrometry system we talked about, right? The star has a planet, it's going around, and it's causing the star to move around physically in space. Right? It's an actual motion effect. So that's true, and if we're looking totally in the plane of the sky, things are going around like this, we see a big astrometric signal. Imagine our system's going around like this, we still see an astrometric signal, but as the star is moving towards or away from you during the orbit, the star is going to be blue shifted or red shifted.
Yeah, so we said it wouldn't be as, we wouldn't be as easily able to detect a planet in this case via astrometry when the system was edge on like that. But yeah, as Ben just said, the light coming from the star is going to be blue shifted and red shifted in a very periodic way that's going to indicate the presence of a planet.
Exactly. So if we can measure that red shift and blue shift, we can find a planet here. And so in the same way as astrometry, there'll be a signal with a period that matches the year on the planet, that the star will move towards us and away from us and back towards us again over the year of that planet. And the size of the signal will depend on the mass, right? The bigger the planet is, the more it pulls the star around, the bigger redshift we see.
Yeah, and that's exactly what we were saying with astrometry. You might remember that the larger the mass of the planet, or the further away it is, or both, the center of mass is going to move away from the star. So if it has to do that, the star has to travel further over the same time period. It's going to travel faster. It's going to shift the signal more. So basically the amount of red and blue shift that we get from this star is directly dependent upon the mass. However, this is really dependent upon the inclination of the system, in that we don't know the mass of the planet for sure. Now, why is that?
Right. So this is a challenge here, that we only, when we talk about the Doppler shift, we're talking about light from the star moving towards or away from you, being blue shifted and red shifted.
Along our line of sight.
Along our line of sight. The radial velocity as opposed to the tangential velocity. But this means that we only see part of the planet's motion, that if the system's perfectly equator on, edge on, we see the star moving towards and away from us. If it's much more polar, most of the motion is not directed towards or away from us. It's this way or this way. And so we only see a little bit of it. So we measure a part of the mass of the planet. We say it's the mass times a function of the inclination, sine of the inclination, if you want to think about the trigonometry of it, or m sine I, we call it. And so when we measure a signal, we measure m sine I, which is a lower limit for what the mass could be. It's the mass if the system's perfectly lined up for us. But if it's more misaligned, the mass is larger, and we don't have a good way to tell from radial velocities alone.
Yeah, you can think of it as if you have a planet orbiting a star and the system is perfectly edge on, you're going to be able to detect the motion of the star based upon the mass of the planet, and you're going to be able to take that full motion. If we were to make it completely face on, you wouldn't know that there's a star, you wouldn't know that there's a planet there based upon the star's motion with radial velocity. So you're going to detect zero mass. So you can think of that as zero mass, that is maximum mass. So anything that we measure, we say is the minimum mass, because it's always going to be at least that up to the maximum mass.
In this scenario, the star is still moving, but it's never moving towards or away from you.
Or radially.
Right, it's just moving around like this, and so we never see the Doppler effect from it.
Well, the Doppler effect, exactly. We don't see the movement in this method, or the effect in this method, but we do for other methods.
Right.
Exactly, which is what we were saying the combination of the methods.
Right.
Is
This is another case where that's important.
Yeah.
If you can measure astrometry and the radial velocity, you have all this information. You have the inclination of the system. You're in business. If you look at a planet through radial velocity and you see that it transits, you know that it has an inclination very near 90 degrees. And so you know the mass in that case.
Yeah. So we can work out the mass. We can work out the period. What other things can we work out?
Yeah, so this one is nice that we actually can get the eccentricity too very nicely. That we don't see that broadly in transits. We get it, in some kind of sneaky ways. But because we're measuring the velocity of the star over time, we really are mapping out the orbit of the star in the ellipse that it's taking as the planet is orbiting it. And so we get the structure of that ellipse, the shape of it, very well. If the planet's on an eccentric orbit, we see that in the motion. And so we know whether the orbit is circular, like most of the ones in the solar system, or very eccentric, like a comet.
Yeah, and as Ben was just describing, if something is in a very almost circular orbit, the speed's going to be almost constant. However, if something's in a highly elliptical orbit, as the planet passes near the star, it's going to move really quickly, and then it's going to slow down as they are further apart. So you're going to see that in the radial velocity curve.
Yeah, this is back to Kepler's second law from weeks ago, that the planet sweeps out equal areas in equal times.
Yeah.
Yeah. So we keep using words like bigger and larger for the signal. Like the more massive the planet, the bigger the signal. It's not a big signal still. This is something that's really hard to do. And there's two reasons. The first is that spectroscopy is expensive, right? It's easy to look at a whole bunch of stars and wait for a transit. We can observe 1,000 stars at once. The instruments we use generally don't enable us to measure spectra of 1,000 stars at once. We have to be looking at the different features in the different absorption lines in the star to see whether it's moving towards or away from us. And so it's something that's much harder to do for a very large sample. So that's one challenge. The second is that it's a small signal. That when we talk about Jupiter around the sun, the radial velocity signal is about 12 meters per second. So that's you could run 12 meters per second, you could sprint 12 meters per second for a little bit. Thing, right?
Maybe.
Yeah, you could start the cycle 12 meters per second. And so we need to measure how fast the star is moving to within how fast you can cycle.
Yeah.
For Earth, the signal is 9 centimeters per second. And that's an ant walking pretty quickly, but it's still an ant or a caterpillar more than a human. 9 centimeters per second is not even that. And so to measure the velocity of a star to that precision means that it's really, really hard. And so we're often looking, we're trying to get down to Earth-sized planets, but it's a very, very sensitive thing. And it takes years because we're waiting for the planet to go around. And so it's a challenging observation.
Okay. Is there anything else we want to say on radial velocity?
I think let's wrap there.
Cool. So we hope that you liked hearing about the main different ways that we detect exoplanets. What we'll be talking about next is chatting about the different missions that have found exoplanets and what we've sort of found, the funky systems that we've found and things like that. So we will see you there. We hope you enjoyed it. And yeah.
Bye everyone.